In this video, I'll be discussing coordination reactions and coordination complexes. So a coordination reaction is just a special type of Lewis acid-base reaction where your Lewis acid is a metal ion. And your coordination complex is just the special name for the product of a coordination reaction. So it's going to be similar to an adduct. Before we talked about an adduct as your product of a Lewis acid-base reaction. Well, a coordination complex is just a special type of adduct that you get from a coordination reaction. So a coordination complex can be described as an inorganic compound which is formed from that central metal ion which is acting as your Lewis acid. And we also have to introduce some special vocab terms here, some special terms that are used for coordination reactions. The first one I want to talk about is ligand. So a ligand is just an ion or molecule which bonds to your metal ion. And your ligands are going to be your Lewis bases in these reactions. So if the metal ion is your Lewis acid, the ligands are going to be your Lewis bases. Ligand is just a special term for them in these reactions. Coordination number. So the coordination number, which you'll sometimes see abbreviated as CN, is just the number that dictates how many ligands can be bonded to your metal ion. So, for example, let's say your coordination number is 4. That means your ion has 4 things bonded to it. And the coordination number will always be given to you. It's not something you have to have memorized because, well, technically the coordination number changes all the time for most of the metals. So because of that, the coordination number will be given to you in the problem. And then the counter ion. So oftentimes coordination reactions are going to give you a charged product, either positively charged or negatively charged. And because of that, you'll need some things called counter ions to balance the charge of the coordination ion. And we'll look at this in more detail when we look at an actual example. But the counter ions are left up to you. You can choose which ions you would rather use to balance the charge. The only thing that is required is that the overall charge of your counter ions balances the charge of the product of your coordination reaction. So let's look at an actual example of a coordination reaction and how you write out the reaction and the product of that coordination reaction. So here's our question. Write the coordination reaction and product for a reaction between a cobalt-3 ion, 1 cyanide ion, 4 ammonia molecules, and a water molecule. And we're told here Cn is equal to 6. So that means that our coordination number is equal to 6. And that means we're going to have 6 ligands bonded to the central metal ion. And that's also kind of given in the problem because 6 ligands are listed out. The 1 cyanide ion, the 4 ammonia molecules, and the water molecule. But if you're ever asked in a question to say what the coordination number is, you just add up the number of ligands you have. But in this case, that was given to us in the question. So the first thing I want to look for in my question is my Lewis acid. And that's going to be this cobalt-3 ion. And remember that 3 in Roman numerals in the parentheses here is your charge on the cobalt. So it looks like we got a 3 in the parentheses, which means our ion here is going to be cobalt 3 plus, because there's a 3 in the parentheses. And now to write out a reaction, we're just going to add up all of our ligands. So we've got our acid, and now we just want to add up all of the individual ligands in the reaction. So the cyanide ion is going to be Cn minus. And there's only one of those. Plus 4 ammonia molecules. So I'll put plus 4. And ammonia is going to be NH3. And 1 water molecule. So that's going to be plus H2O. So to write the product of a coordination reaction, start with a bracket. Always want to start with a bracket. And then first thing you want to write is your metal. In this case, our metal is cobalt. And then after you write your metal, you list all of your ligands in parentheses. So I'll start with my first parentheses with cyanide. And I only have one, so that's all we need to write for the cyanide. Then second parentheses, I'll put the ammonia. So we have NH3, and then after you close the parentheses on your ligand, if you have more than one of that particular molecule or ion, you'll want to list how many there are after you close the parentheses. So we have 4 ammonia molecules, so I'll put a 4 like that. And then our last ligand would be the water. So H2O. And then that's our last ligand, so we'll close the bracket. But now we have to worry about the overall charge. So to calculate the overall charge, just add up the charges in your reaction. So we start with a +3 charge, and then the cyanide has a -1 charge, so we subtract 1, and then ammonia and water are both neutral, so they don't really contribute. So really all we're worried about is this +3 and this -1. Well, 3 minus 1 is 2, so our charge is going to be 2+. That's your overall charge for your coordination ion. So if we went through and labeled everything, this cobalt 3+ would be our Lewis acid. These 3 guys here would be our 3 ligands in our reaction, our Lewis bases. And this product here is going to be our coordination ion. But you'll notice, as we said before, this ion has an overall charge of +2. So we're going to need some counter ions to balance this charge. And like I said before, it's up to you which counter ions you choose. The only rule is they have to add up to balance the overall charge of your coordination ion. So if our charge is +2, that means we need a total of -2 to balance the charge. So you could do, for example, 2Cl-. That would give you a -2 charge, which would balance the +2. Or you could do SO4 2-, because the sulfate ion has a -2 charge, which would balance the +2 charge. So it's really up to you. You just have to choose one or more ions that add up to balance the charge of your coordination ion. You want the charge to be 0 after you add your counter ions. That's really the only rule. So now let's take this a little bit further and look at how else you could see this asked. So you may be asked to draw the coordination complex and state the geometry. So to draw it, just take your coordination ion and draw what's called a stick and ball configuration. So you can either do it based on Lewis structures, or you can draw the stick and ball. In this particular case, I'll just do the stick and ball. So you'll want to put your metal ion in the middle, and you'll just draw the different ligands you have coming off of the central metal ion. So, this is, my best artistic rendition of what this coordination complex would look like. You definitely don't have to get overly fancy with this, I mean, if you wanted to draw the Lewis structures too, that's fine. Or if you wanted to draw the stick and ball configuration, that's fine too. Either one works. You just want to get the general idea across, right? So we have our cobalt in the middle, Right here we have our cyanide ion, so the C and the N coming off on the top. We have our 4 ammonias going around. So we have an ammonia here, 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 and here. And we have our water down here coming toward the bottom. And remember, it's a charged ion, so we have our charge out here. And then just put your counter ions, just write them outside the brackets, you know. Here I'm just balancing it with 2 Cl- ions, and that's going to be the total of my counter ions. So that's how you would draw it. But what about the geometry? So coordination geometry is going to be very similar to electron geometry. So if you have 6 groups coming off of your central ion, so here we have 6, that's going to be octahedral. And the geometry is going to be determined by your coordination number. So if your coordination number is 2, your geometry is linear. If your coordination number is 4, your geometry is tetrahedral. If your coordination number is 6, then your geometry is octahedral. And those are the most common ones. 4 and 6 are definitely by far the most common coordination numbers. So tetrahedral and octahedral are going to be your most common coordination geometries. In this case, it was octahedral. So that just about wraps up coordination complexes. And in the next video, we'll actually look at nucleophilic substitution, which is another kind of Lewis acid-base reaction.